Okay, we're going to continue our discussion on chapter 5, equations, inequality, and application involving root functions, power properties. Let's take a look at this one. If P and Q are algebraic expressions, then every solution of the equation P is equal to Q is also a solution of the equation P to the power of n is equal to Q to the power of n for any positive integer n. Now you have to be careful with this. This probably doesn't say that the two equations are equivalent. The new equation may have more solutions. For example, if I have x is equal to minus 2, x squared is equal to 4, then in this example you would get x equal to plus and minus. So here you get two solutions where the beginning we had started with x equal to one solution minus 2. We're going to look at more examples of these now. But let's take a look at these steps, how to solve equations that involve root functions. Step number 1, you may want to make a note of all these. That step number 1 is to isolate the terms that involve a square root in there. If you see square root in your function, you isolate that. That's step number 1. Where it's possible. Sometimes it's not possible to isolate, but if it's possible, you move that to one side of the equation. And then step number 2, raise both sides of the equation to the power that eliminates the radical. So if it's a square root, you raise it to the power of 2. If it's cube root, you raise it to the power of 3, and so on. For step number 3, then you solve the resulting equation. And step number 4, you check the answer. So let's take a look at some examples. This would be an example where we can isolate the radical, because I have radical 11 minus x on the left-hand side. Then I have this minus x, which I can move it to the other side. That's how you would isolate the radical. So you would simply add x to both sides of the equation. Right? In this case, you get square root of 11 minus x equal to 1 plus x. I isolated the radical. Step number 2, and we remember what's step number 2? What power is that? Raise both sides of the equation to the power of what? 2, because that's the square root, right? If this were cube root, then raise it to the power of 3. Because this is square root, we raise both sides of the equation to the power of 2. That's how you will eliminate the radical on the left-hand side. In the right-hand side, you get 1 plus x squared. We know how to expand that. First term square plus 2ab plus second term square. And then now you can see you don't have any radical here anymore. We isolated the radical and we eliminated radical at this point. So now I'm going to move everything to one side of the equation so I can factor them if it's factorable. If not, I use a quadratic formula. Looks like it is factorable. We get x plus 5 times x minus 2. So we get x equal to negative 5, x equal to 2. Are we done? The last step is very important with equations that involve radicals. The last step is to check, see if there indeed is a solution or not. And we can easily do that by substituting for each x minus 5 and see if it makes sense. If I substitute for each x minus 5 into the original equation, that doesn't make sense. It's false. So minus 5 is not a real solution here. However, 2 is. If I substitute each x2, then you can see, yes, 2 is the answer, but not minus 5. We only get one solution here, which is 2. The graphing solution would be to graph these two functions on the same x and y axis and see where do they intersect. And as you can see, would intercept at the same point that we calculated too. Let's take a look at this example. Solve x minus 5x to the power of 1/2 plus x equal to 1. This is really the square root problem, right? Remember, because power of 1/2 means the square root. So I'm going to isolate that first by subtracting x from both sides of the equation. And then I have to raise both sides of the equation to the power of what? Still is second root, it's 2. And that's more clear, actually, why we raise it to the power of 2. Because 1/2 times 2 is equal to 1. So here we get 5 minus 5x is equal to 1 minus x squared, which is, you can expand that to first term square plus minus 2ab plus second term square. I'm going to move everything to one side of the equation, see if we can factor this. If we cannot factor, then use quadratic formula. In this case, it is factorable to get x equal to -4 and x equal to 1. Don't forget to check your answer for both of them. And the graphing solution would be if you graph both of these functions on the same x and y axis, and you clearly see that would intersect at 2 points, -4 and 1. Let's take a look at this example. Now we have cube root of x squared plus 3x is equal to cube root of 5. Now this is rather simple because both sides is cube root. If I raise both of the equation to the power of 3, I can eliminate the radical from both sides of the equation and get my second order equation. Now in this case, it's not factorable. I'm going to use a quadratic formula. So you get two solutions, x equal to -3 plus radical 29 over 2, x equal to -3 minus radical 29 over 2. You get these two solutions. Let's take a look at this example. Can I isolate the radical now? No, I cannot isolate radical here. So remember I said sometimes you cannot isolate radical. This would be the example. So if I move square root of x plus 1 to the right, it won't be isolated because that would 1 next to it. And if I leave it the way it is, it's still not isolated. So when you cannot isolate, at least move one of them to the other side, in this case. And then what you need to do is you need to square both sides once and then simplify and then square again. You have to do this process twice. If I square both sides one time, I eliminate the radical on the left-hand side. But when I expand the binomial on the right-hand side, the middle term 2ab would contains radicals still. So then I can isolate the radical and then square again. So you have to do it twice when you cannot isolate the radical. Once you isolate finally, you move everything to one side of the equation and factor them and look for the solution. And make sure you check your answer at the end if indeed they are the real solutions. And when you check this, it shows that -1 and 3 are the solutions. Let's take a look at this example. Solve the inequality. Here we have cube root of x squared plus 3x less than or equal to cube root of 5. Very similar problem. We did this problem already and we find the solutions to be at this point, -3 plus and minus square root of 29 over 2. So if I go and use my graphing calculator now and graph this, you can see at what point your graph would be below 0, at what point your graph would be above 0. You're looking at less than 0, so we're looking at the point where your graph going to be below 0. So from this point, this 2 point of intersection that we found using the quadratic formula right here. So all the number in between these 2 points, your graph would be below 0. In other words, less than 0. If they say greater than 0, so then you go from -infinity to this point. From this point to positive infinity, these would be the solutions if it was greater than 0. Solve the inequality here. If you remember, we solved this equation before and we got the answer -1 and 3. So if I plug that number into my calculator and graph them, you would see they would intercept at the point 1 and 3 as -1 and 3 as we calculated before. Now you want it to be greater than 0, so you look for where your graph is above 0. Your graph would be above 0 from 3 all the way to infinity. If it says, show me where the graph is below 0, less than 0, then it would be from -1 to 3, but above 0 would be from 3 to infinity. Just by looking at the graph, we can find the solutions. Now, this one is also the equation that involve negative exponents. Remember, negative exponents is 1 over something. So we have, this is really 15 times 1 over x squared minus 19 times 1 over x and so on. Remember what we did when we wanted to eliminate the fraction? We multiplied them by LCD. So this is really is 15 over x squared minus 19 over x plus 6 over 0. It's the same problem here. So the LCD in this case among all these would be x squared. If I multiply them by x squared, I would eliminate all these fractions. As you can see, x squared times x to the power minus 2, that would give you x to the power of 0, which is 1. So at this point here, all the fraction disappears. There's no negative exponents. And then there we can factor this and solve for it. You get x equal to 3/2 and x equal to 5/3. So these are my solutions. Let's take a look at this example. 2 times x to the power of 2 over 3 plus 5 times x to the power of 1 over 3 minus 3 is equal to 0. This is known really as solving by, anybody remember the method? Substitution method. Remember substitution method? When these two terms are square of one another, we can use substitution method. So you can let x to the power of 1/3 be equal to maybe w. The other one would be w squared. So in this case, we're really letting x to the power of 1/3 be equal to another variable. In this case, I use u. So if I square that, then would be x to the power of 2/3. So when these two terms are square of one another, we can make these kind of substitutions. So really we have 2 times u squared plus 5 times u minus 3. So we're forcing this to be a second order equation by making this substitution. So we can factor this now, it's factorable, solve for u. But remember, we're solving for x, not u. You have to go back to your original assumption that u is equal to x to the power of 1/3 and solve for x. So for each of these, you're gonna let u be equal to x to the power of 1/3. So 1/2 is equal to x to the power of 1/3, -3 is equal to x to the power of 1/3, and then you solve each of those, and you get x equal to 1/8 and x equal to -27. It's called solve by substitution method. These are my solutions. Solving equation with rational expressions continues. Complete the following. Write the equation. This is the expression. Write the expression without any negative exponents. That's step number 1. And then we're going to use part A to solve this equation. Let's take a look at the first step first. So in this case, we're going to multiply both the top and bottom of the fraction by x to the power of 1/3. Why x to the power of 1/3? Because -1/3 times, when you have x to the power of -1/3 times x to the power of plus 1/3, you add the exponents, right? -1/3 plus 1/3, that adds up to 0. That would be x to the power of 0, which is equal to 1. So that's what we're going to do. Because x to the power of 1/3 times x to the power of -1/3, that would be just simply 1. And that's what we really want. We want to eliminate those negative exponents. So if I multiply each term by x to the power of 1/3, that would assure me to eliminate all those negative exponents. That's the first step. And as you can see, this would become 2/3 times x plus 1. This 2 would be equal to simply 1. And here we just add the exponents. So we add the exponents here. 2/3 plus 1/3, that gives you just 3/3 or 1. Everything nicely falls apart here, and we would eliminate all the negative exponents that way. So we get 2x plus 2 minus 3x, you get 2 minus x at the top. And for part B, it says solve that. When you solve this, you let it equal to 0. When you let it equal to 0, the bottom term really doesn't affect anything here for solving x. So you really, what you worry about is the top, because if it's like a proportion, would be 2 minus x is equal to whatever we have at the bottom fraction times 0 would be 0. So x would be equal to 2 here. One solution for that. This is a good example to see one of the application for this section. Here is a company wishes to run a utility cable from point A, which is right here, to, which is on the shore, to an installation point B, this island here. So we want to move some cables from this point here, A, to this island point B. Part of these lines going to be on ground, and the other one would be under the water. And there are different costs associated with the cable that runs on the ground or underwater. It costs $400 per mile to run the cable on land, and $500 per mile to do that underwater here. So also they're giving us that assume that the cable starts at point A and runs along the shoreline, then angles and runs under the water, as you can see in this figure here. So we're gonna let X represent the distance from C, point C, at which the underground portion of the cable runs begins. So this would be a good illustration of what we're doing. And the distance between A and C is given to us as 9 miles. So this is the good information. The distance from A to C is known as 9 miles. You know that. So as you can see, if I run my cable from point A on the ground from here to here, and then run it under the water from here to here, I'm just going to call this K. So if this whole thing is 9, and let's say this distance is X, I don't know what it is, this distance would be 9 minus X. So the restriction should be pretty obvious here. X must be greater than 0, and also 9 minus X must be greater than 0. So that would be my restrictions that I have. So X must be greater than 0. Also, 9 minus X has to be greater than 0. So that would be, it means X has to be between 0 and 9. That's a restriction that we have. Now, to solve K, I can use the Pythagorean theorems, because that was a right triangle, if you recall. K squared is equal to 6 squared plus X squared. Let's go back to the figure again. K squared is equal to 6 squared plus X squared right there. And from there, I can solve for K would be equal to square root of 36 plus X squared. K is greater than 0. So I'm finding K, the distance K, in terms of X this way. So I'm going to write my formula, the cost that it takes to come up with these cables would be 400, that was $400 per mile, and that would be where you use on ground. So with that, we figured is 9 minus X is the distance for on ground, plus $500 would be the cost to run the cable under the water. So we already figured that distance in terms of X by using the Pythagorean theorem. So this would be my cost equation. So here it says for this part, it says if 3 miles of cable are on land, then we just substitute for that amount. We know 9 minus X equal to 3. So then we can find X would be equal to 6. So the cost would be finding a CL cost for X equal to 6. So just substitute for each X6, and that would be the cost it would for this condition, $5,442.64. And then we can easily use our calculator to find the minimum value. For this part, you can plug the numbers, the equation in your calculator, and find the minimum point, which turns out to be at X is equal to 8 in that interval. So the minimum value of the function occurs at X equal to 8. So 9 minus 8 would be equal to 1 mile. Should be long for the land, and then you can put the values for K. That would be 10 miles under the water. And actually we can find the cost of that by letting X equal to 8, and that would be the minimum value for cost for that condition. And your calculator actually can evaluate that as well by using the numbers here. For F minimum would give you that value right there on your calculator.